Oops. All right. Hello and welcome. Today is April 20th, Monday. We're pretty much 1 month in now to our online classes. We have about a month and a half left with school, so we're almost at the finish line. Now, 3 weeks before the AP tests. So we have, well, you guys have slightly more time because your test is on Thursday. So you're well into the AP testing week. So you have slightly more time, 3.5 weeks for you guys to prepare. Today is April 20th. There we go. And it is finals review number 7, the last of our finals review series, which is on, what is this? Rotational Dynamics. And this is the last part. Now. Well, Unit 7 kind of covered waves along with shim. It is possible that at least spring energy, those types of concepts could be on the AP test still, because they're technically not into mechanical waves yet. So when the College Board says mechanical waves, they're talking about actual, when we actually dive into Unit 7, talking about sound and everything else. Now, you can have mechanical waves with spring mass systems. But, you can do so much with spring mass. It's not just about waves, so at least the concepts should be there. Now, if you're going to prepare for your final, you might as well know all of Unit 7. Don't just start throwing things out. Keep everything together. Keep your binders together. They'll be a great resource to use, as it has everything that you could possibly need, right? You can see more and more are joining us as people are waking up. That's good. Throughout the next several days, well into next week, really, we'll have random, small quizzes, very small quizzes, but we will do them. And of course, I will open up the, well, I guess it's already open, but the multiple choice in the My AP College Board section will also be opened up, and then we will actually make it mandatory. If you've already worked on the My AP multiple choice questions, great. Keep it up. We'll get some participation grade out of the College Board multiple choice stuff that's there. Now, the FRQ, you won't get, obviously you can't get it graded. You can check the rubric and stuff. We can go over certain FRQ questions that I think may be on the AP test. But other than that, there's no instant feedback for FRQs. But there is for the MC. At least you'll know how many you got. So anyway, that's the plan for the next 3 weeks. This week we'll finish up our note-taking, and then we'll do a couple of quizzes. At least 2 this week. 2 small ones. Alright, so let's begin with the rotational dynamics. It's not really UCM, it's actually, your WOAT stuff. Recall that theta, theta, your angular displacement, measured in radians, rad. We got delta theta, or I'll use delta theta per time, so radians per second is your angular velocity. I should write omega first. Is omega And since we took deltas, this is technically the average. If I took instantaneous, time in the denominator, or I took the derivative d theta dt, I would get the instantaneous omega. Of course, we can do the slope or the derivative once again. So slope of the slope. These are alpha, and this is average alpha. Radians per second squared. Now, having alpha means that your centripetal acceleration is constantly changing, right? We can relate each variable using the arc length formula, s equals r theta, or x is equal to radius times theta. Right, and then you start taking the derivative on both sides, you get v equals omega, and a equals ralpha and omega. These are tangential quantities, v tan, a tan. So these are tangential velocity and tangential acceleration. Recall that if I am some r away, we have a tangential velocity depending on which way I'm spinning. Let's go and spin positively, which is counterclockwise. The centripetal acceleration points towards the center, and it's equal to this tangential velocity v squared divided by the radius. Now, since v is equal to omega, we can see that we get omega squared over r, which is r omega squared. Okay, and so with a non-zero alpha, omega is constantly changing, which means that centripetal acceleration will be changing. A non-constant centripetal acceleration, which means the centripetal force must be changing. So be careful with alpha. You should know all of your kinematics equations with these rotational variables. I'm going to skip over that. Take a look at your notes for Ralph, Mitch, Dom, and Lou. So those are the 4 kinematics equations. Technically there is a 5th one, we just don't really need it. And the Schroeder equation, I wonder what the Schroeder is for here. Could it be Stanley? Stan. Ralph, Mitch, Dom, Lou, and Stan. We don't talk about Stan. Now, of course, torque. Oh, we got one person to laugh. Excellent. We did it. It's a tough crowd today. No one is in a cheery mood, it seems. You should be happy. I mean, the stock market is going up. People are thinking things will return to normal. But of course, you have a bunch of people protesting about the lockdowns. and they're trying to get back to normalcy before we're even ready. In other states, at least, not ours. Torque is your rotational horse. R cross alpha. Some big brain people out there, yeah. Okay, when you apply a force radially away from your axis of rotation, then you cause a torque. Now use right hand rule for direction. And you can use the right hand rule for both omega and alpha at the same time. Let's see. Here's my thumb. Oh gosh, this is going to be hard. Let's see if I can do this. Here's one of my fingers. 2, 3. If I were in The Simpsons, I'd be done with 4 fingers. But in real life, I need one more useless digit. Actually, it's not very useless. I guess your little toe is technically useless, and if you cut it off, you won't be losing much. But pinky is actually used quite a lot, right? If you're a gamer, your pinky is probably doing all the control and shift and other things. And if you have buttons on your mouse, in your right hand, you're probably using your pinkies to push those buttons. Is R a vector too? R can be a vector. So the R vector is outwards from the center. That's the direction of R. Okay? When you take cross products, you have to have 2 vectors. You can't take a cross product of a vector and a scalar. Therefore, inherently, R must be a vector. Look at that. Look at that thumbs up. I think the thumb is kind of big, but that's all right. We got a big thumbs up. And the thumb is the direction of your torque. It can also be the direction of omega. I'll just leave it as torque, but you can also use you give that thumbs up a thumbs up. Excellent. And the curl of the fingers, let's see, curl. So when it curls this way, of course you want to look at it from a helicopter point of view, from the top. You want to look at it from the top, so the thumb is coming towards you if you look at it from the top, and you can see how your fingers are curled. In the direction of the curl is the force, really. It's how the force is curled around. I'll just call it the spin. Uh-oh. Okay. Now, when I say spin, it is technically the direction of the acceleration of the spin. Right. Okay, so if you're speeding up in that direction, then definitely torque is the thumb. But what if you're slowing down Now if you're slowing down, your alpha is the other way. Or in other words, your force is being applied in the opposite direction. And so follow the force. Follow force when you do your right hand rule. So let's see. Let's have a wheel. There we go. And let's say it is spinning clockwise but slowing down. I should use a different color. I'll use purple. Clockwise but slowing down. Now, if it's spinning clockwise and slowing down, how do I stop this wheel? I'll have to apply the brakes. So what are brakes? Brakes are typically a little disc or a little piece of ceramic or some other material in combination. And when you hit the brakes in your car, you are applying a force, this pad. If I look at it in 3D now, so imagine the disc being like this. And so this pad, usually not touching, gets a force, applied force, Fa, that is pressed against the surface of your wheel as it's trying to rotate. Oops, I should do it the other way. As it's trying to rotate around its axis. And this applied force causes a normal force onto the wheel, etc. A surface, the two surfaces start producing heat due to the friction, and all of that will take away the kinetic energy and slow it down. Okay. So we have a clockwise that is slowing down has a counterclockwise torque. I should say counterclockwise. Oops. There we go. So the torque must be in the opposite direction, a counterclockwise alpha, if you will. So CW alpha, that is slowing it down. Now, the clockwise and the counterclockwise, those two terms only talk about the spin itself. It doesn't actually tell you the direction of your vector. Okay, so we use the right-hand rule to denote the direction of the vector itself in space. So it's slowing down, therefore alpha is the other way. And so we orient our fingers. If we orient our fingers in this counterclockwise direction, so take a look at your fingers. It's either going to be thumbs up or thumbs down. And you can see in order to get this counterclockwise alpha, which means that the torque is going to be in the same direction, then we get a out of the page torque. Okay. And since torque is out of the page, yes, the alpha is also out of the page in space, at least. The direction in space, the direction of the vector. And that's because torque and alpha are also related, similar to how force and acceleration are related. Okay, we say that torque is I alpha. And so torque is the direction, is the vector. Ooh, that is not a very good vector hat. I'm falling off my chair. I need to fix myself. There we go. Torque is the vector and alpha is the vector. I is not. I is the moment of inertia, not current. Now, luckily for you guys, Unit 8 is not on the AP test. Currently, I is inertia. You get it. Moment of inertia And the general form for the moment is mr squared. So that's the general form. And of course, as you know, different shapes have different values. Okay. In next year, you'll see it as an equation where it's the integral of r squared as a function of mass dm. So you need radius as a function of mass, and then you can take the integral. So all sorts of fun stuff we're going to do next year. Seniors, well, best of luck. Consider taking physics in college to learn more. So this will be an APC. All right. So with a disk, we know a couple. So have those simple ones memorized. Yeah. Now, typically, in your undergraduate, or what are they called? Yeah, they're called lower division classes. You do have a physics like 101 and stuff, but those are like very generic, general physics courses. So you'll see that they divide the physics courses out depending on your major. So if you're going to be like a biology major, you actually have like a lower end physics that you have to take. But if you're like an engineering major or a physics major, you'll have to take like a higher end physics. So the numbers could be different depending on your major. We know disk. What is a disk? Well, a disk is like a very small cylinder, really. A cheese wheel, there we go. Yeah. That's 1/2 mr squared. R being the radius, and the thickness of the thickness doesn't actually matter. So if you had like a giant cylinder, and it's rotating about the same z-axis, so it's rolling about this z-axis here. Ooh, that's not very good, is it? Oh my gosh, I didn't want that. There we go. No! I should draw it this way. There we go. Why does it look all weird? There, that's the one I want. So it's about the z-axis, then the moment of inertia is the same. Yeah. Your hollow version, which is a hoop, now has all of the masses radius r away. So how do I draw a hoop? Let's see. Oh, it's not that bad. Is it? I don't know. It's kind of bad. Let's see if I can use ink to shape. Boom. Oh, okay. If I shade this in, now it's definitely 3D. There we go. A hoop. Voila. Now the hoop is 100%, meaning just mr squared, which is the same as a ball on a string, point-like particle. aka ball on a string, massless string. Where all of the masses radially are away. Right? Okay. Now what if you had two strings and two balls and you're spinning them around similar r distance away, and you're spinning both of them around? Or it could be like a massless rod with two masses on each end. Well, you can say that the total inertia is just the sum of the individual inertias. So you can do a sigma inertia equation, sum of all inertias. And so it's mr squared plus mr squared in this case. Oh, that's not a square, that's a 2. There we go. mr squared plus mr squared. All right. And we have like solid ball, and hollow solid sphere. Whoa, what is this? What's the moment of inertia of the black hole, of a black hole? Assuming it's a spinning black hole. If you'd like to learn about the different types of black holes, consider waiting until we watch Interstellar. And then you can learn more. Okay, so this is a solid ball. Solid. And that is solid sphere. The solid one obviously has less inertia because more of it is distributed throughout the system, and some of it is closer in towards the axis of rotation, so it is 2/5 mr squared. It's less than having a flat disk rolling around, so a ball-shaped wheel would have less inertia than a disc-shaped wheel. Alright, anyone remember the hollow? The hollow ball. Hint, similar to a hoop, it should be more. Should be more. Two-thirds. Yeah, we can start deriving these next year with actual calculus. Okay. Yeah. All right. So that's moment of inertia stuff. Consider rolling down ramp problems. We have rotational inertia, etc. All those types of rotational energy. Ke rot is equal to 1/2 I omega squared. Okay, and don't make silly mistakes where when you substitute, make sure you substitute them one piece at a time. Use parentheses mentally or actually. when you're substituting. The I has a squared, and recall that we can use V equals omega to translate between regular kinetic energy and rotational kinetic energy. If you're rolling without slipping, then V equals omega. If you do slip, if you're doing a burnout, or if there's just not enough static friction, then V does not equal omega. Okay. So when we're rolling around, typically we have the velocity V, velocity 2V, and the velocity 0. So that's rolling without slipping. And so it is the static friction force that is providing the torque on the system. So there's this friction that's providing a torque that is spinning it, right? This is rolling. Now, a car wheel, on the other hand, is slightly different in that the axle is providing the torque. Yeah, you assume rolling without slipping, unless it's stated in the problem, it's going to be rolling without slipping. Yeah, in AP1 at least. So a car axle is the one that provides the torque on the wheel, and so it's different in that the wheel will turn due to the torque provided by the axle, and friction goes the opposite way in that it stops it from slipping around. So friction gives you traction, and then this forces a Newton's third law effect to occur, which means that the car moves forward instead. Anything that is rotating around also has angular momentum. L which is equal to I omega. And L is a vector, of course, and it's in the same direction as omega. Right, chat, how do you find the direction of omega if you were paying attention? Yikes. People be sleeping. Fast butter. I love physics. Little Huister. RHR. Very good. We have some new people in chat. Or maybe I just never noticed. Use the right hand rule, yeah. Angular momentum is conserved unless acted upon by an external net torque. Unless acted upon by a net external torque. So this statement is very important, especially this word net, which is total. You can be acted upon by external torques. If those external torques cancel each other out, then your angular momentum is conserved, even though you're acted upon by an external torque, right? It's just that if there is a net torque, net external torque, which means out of all the external torques that are applied, if by adding them together you get a non-zero value, then now your angular momentum is not conserved. So a little minor detail that could change everything, really. So pay attention to such statements. So if you're asked a question where you have to justify if a certain person made, like, how in tippers you have like student A says blah blah blah, and so pay attention to words like net. So if student A just says, oh yeah, of course, angular momentum is conserved unless acted upon by an external torque. Well, no, technically no, that is not correct. You can still conserve momentum if you are applied by external torques. It's only when the net torque is 0 that's when it's conserved. All right. Let's see. Let's do some quick interactions with dynamics. So here's another one of our problems. Here it is. It says 3 identical wheels are mounted on frictionless bearings. So at the center you would have your windmill thing. So just like the windmill, these are classic physics problems. A classic physics problem. All 3 wheels have equal lengths of string wrapped around them. Wheel A has 4 1-kilogram masses attached to its spokes near the wheel's center. Wheel B has 4 1-kilogram masses attached to its spokes near the wheel's rim, while C has no masses. Ooh. In each case, write the letters A, B, and C. If any cases are equal, indicate by putting an equal sign. Rank the 3 cases below based on which mass reaches the floor first. All right. All right. So we're going to let them spin. Kind of, it's basically like the windmill thing we did in class. We'll let it spin. So as this mass falls, this thing is spinning. Of course, the interaction is that based on its inertia, it's going to spin at different rates. The one with more inertia will spin slower, therefore dropping the mass slower at a slower rate. The one with less inertia would spin the fastest, right? All right, chat, go ahead and rank A, B, and C based on which one goes down first. Ugh, I need to drink some water. We got Noah with the RHR. CAB, cab. Cab, perhaps. All right, so we're looking at 3 wheels. One of them has lots of mass inside. Ooh. Mass, 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 mass. The other one has mass on the outside. And if you remember from your lab, of course, when mass is distributed, or your test question, when mass is distributed further away, it has more inertia. Now this one here at the end has no mass. So what's better than having mass closer in towards the center? Having no mass at all. Nothing at all. Nothing at all. It's a Flanders reference. Stupid Flanders. C, B, oh, whoa. Ink to shape destroyed my B. B, A. Alright, yeah, so C is less, so we're going from least to greatest, right? Oh no, we're ranking, we are ranking which one reaches the floor first. So C reaches the floor first, and then A, and then B. Okay, so that's because the mass that is hanging, if I did an FPD on the mass, we have mg down and tension force up, and this tension force applies a torque on our wheel. And if I did an FPD on the wheel now, let's see, Recall that when we do FPDs on wheels, especially ones that are spinning, we want to draw the force where they are applied on the body. So if this is the axis of rotation, then the force is 90 degrees or tangent to the surface of the wheel. And you can see that this tangent vector is 90 degrees to the radius vector r. And so we get 100% torque. Right, so we do a sigma tau equation. Sigma tau tells us that the moment of inertia times the angular acceleration of the wheel must equal the radius cross radial arm cross the tension force. And the cross product gives us sine of 90 degrees. And sine of 90 degrees is just 1. So we can say that it's RFT. Okay, we're taking the angle between the radius vector and the force vector. Now, if you had forces that are at weird angles, so pay attention. You know, sometimes you get those ranking questions with forces at different spots, right? That's another classic mastering physics type problem, where if you had a force that is applied, you know, halfway versus a force that is applied all the way, of course, with a bigger radial arm, you're going to get more torque, right? That's why you want to use a big wrench versus a small wrench. Well, a bigger wrench will give you more torque on your nut or screw that you're trying to get out, with the same amount of force that you yourself are applying, right? If you're trying to take off the, if you're trying to, you know, replace your flat tire, right? You want to extend the radial arm as much as you can, and that will apply more torque on your bolt. And pay attention to weird angled. So of course, if it's tangent, it's still tangent, right? It's still 100%. But if it's not tangent, so let's do one that is not tangent. If it's not tangent, ooh, that's not a very good color. Let's use light blue. If it's not tangent, what do you do? Okay, well, what you could do is find the tangent vector. So if this blue one was F2, then we would draw the vector components, and based on what this angle is, now these two angles are supplementary. We'll call this theta 1, theta 2. Oh, I can't really see. Theta 1, theta 2. Of course, theta 1 plus theta 2 is equal to 180 degrees. There are supplementary angles. And so what we could do is just find the components. This would be F2 sine theta 2. And F2 sine theta 2 would be 90 degrees to the radius vector. Right? Luckily for us, the sine of theta 2 would be equal to the sine of theta 1. Is this true? Well, is this true? Is sine of 20 equal to sine of 60? Oh, so 160? Probably. Probably is the answer. All right, so back to our problem. How do I get alpha? Well, we can use the sigma F equation instead of the torque equation. We'll use sigma F equation from the falling mass, and this tells us that the tension force minus mg is equal to ma. Now we also have to worry about the direction and stuff, the direction of the torque. Is this a clockwise torque or a counterclockwise torque? Technically this is a clockwise torque, right? The wheel would be spinning this way. So if it's a clockwise torque, clockwise is the negative direction. So minus negative I alpha equals RFT. Okay, where FT, notice how FT is a positive number. Okay. That being said, then we do a relationship between alpha and A. Normally A is equal to alpha. But if A is a positive number, then is alpha a positive number? So let's take a look. Ft is equal to, oops, there we go. Ft is equal to mg plus ma. Isn't A a negative number? Yeah, so since A is a negative number, okay, Ft is going to be less than the weight of the object, mg. Right? Since A is a negative number, notice how it turns in a clockwise fashion, so A must equal alpha. I'm not adding. When you write sigma equations, the right side of the equation stays normal, so you don't mess with the right side of the equation, unless you have like a pulley system and two masses are like connected via pulley, and you know one of them is accelerating positively and the other is accelerating negatively. That's when you put negative signs and other stuff in front of the ma. But otherwise, you leave the ma alone. Okay. Your outcome will tell you what the values are. Okay, so here we have a tug of war between Ft and mg, and it is still equal to ma. It doesn't mean A is a positive number when I say A equals ma. A could be either positive or negative based on the outcome. Okay, since we know it's going down, we know mg is going to win, therefore A will be a negative number. If I set A as a positive number, then I would have to put a negative sign here instead. And if A was a positive number, then this A equal alpha thing would not work, right? If A was a positive number, then I would have to say A is equal to negative alpha, meaning a positive number generates a clockwise angular acceleration. So the reason why since I left it like this, I was able to say that A equals alpha, and I was able to put this negative sign. Ooh. So let's see if this works, right? Notice how A is a negative number, this will generate, if alpha is equal to a over r, if a turns out to be a negative number, then this will give us a negative number for alpha. And when I plug in a negative number into here, the two negatives will cancel out, and our force of tension will be a positive number, right? So this makes everything work. We started with Ft being a positive value because it's going upwards. Okay, so let's take a look at a situation where we don't where we do change the right side of the equation. In a massive pulley, where your pulley has mass and it's not ideal, M1, M2, we'll just say it's frictionless. So what changes? Well, if you have MP and RP, MP being mass of the pulley and RP being the radius of the pulley, then the two tensions are different. There's a tension 1 this way on the pulley, and there's a tension 1 this way, or tension 2 this way on the pulley. That same tension force is pulling mass 2 up, and that same tension force is pulling mass 1 to the right. Okay, remember, forces internally inside a string or a rope, the tension is just a value. It's okay. It doesn't matter which side you're at. So if you're playing tug of war and you're pulling on a rope, okay, it's true that one person could pull the other more or less or whatever it is, but the Newton's third law tells you that for every action there's an opposite equal reaction, right? So if you're pulling harder, that means you're being pulled by the same amount, assuming that there's enough friction between you and the ground. Okay. The tension inside the rope, no matter which side is actually doing all the pulling, doesn't matter. The tension inside the rope is the same value. Okay. You don't win because you're pulling harder. You win because you have more friction. So if you have better friction between your shoes and the ground, then you're more likely to win the tug of war. What can you do besides buying better shoes, grippy shoes? Well, you can angle yourself, lower your center of mass so there's less torque on you. If you are angled downwards, you're kind of cheating, but that's all right. If you're angled downwards, I guess. You can kind of build up some dirt, turn the dirt into a wall, and then apply your forces on that dirt part. So those are the small hacks that you can do to win a tug of war. There you go. Apply your physics. It's not cheating, it's just you're using better physics to win the game. Here you would do different sigma equations. We're saying that Ft2 is a positive number. Ft2 minus M2G is equal to M2A, where here I would put a negative sign to denote that M2 is going down, and since we're connected via pulley, we have to do this. Okay. For M1 in the x-axis, tension 1 pulls it to the right, and since there's no friction, there's nothing else. And it's equal to M1A. If there was friction, then you would do minus FF, FT1 minus FF. And so M1A moves to the right. And notice how, even though the tensions are different, okay, one of them is definitely winning. Which one is winning, chat? Which force is stronger, FT2 or FT1? Hint. Which way is the system accelerating? For every chunk of rope that moves forward to the right, an equal amount of chunk moves downwards. Yeah, number 2 is stronger. It's winning the tug of war here. And it would spin. Now for our pulley, we have 2 tensions, FT1, FT2. These two provide 2 different torques, so we'll do a sigma tau equation. This is sigma F2. This is sigma F1. In the torque, we have clockwise minus counterclockwise. So, no, I said that backwards. We have counterclockwise minus clockwise. Counterclockwise is positive. So tension 1 goes counterclockwise. So the counterclockwise torque 1 would be the radius of the pulley, RP, times tension 1. And it's because it's tangent. We know that it is 90 degrees, so we don't have to worry about the sign. Minus radius of the pulley times tension 2, FT2, and this is equal to I alpha. Okay, I leave I alpha alone here. And I just set up an equation for A and alpha. So does A equal alpha? Well, when A is a positive number, is it a positive number? Based on the way I wrote down my sigma equations, A is a positive number. I am assuming that A is a positive number because I know that M1 is going to go to the right, especially because there's no friction. So A is a positive number. It pulls M1 to the right. M2 is going to go downwards. Okay. And so when A is positive, does the pulley spin clockwise or counterclockwise? Okay. As the system evolves, the pulley spins clockwise. And therefore A must equal negative alpha. So when A is a positive number, I need alpha to be negative, such that alpha is equal to negative A over R. Yes, clockwise. Good job, Megan. All right. Finally, with all that tangent, let's finally get back to our question. Part B, rank the 3 cases below based on which wheel has the greatest angular acceleration as the mass falls. Right? So that's no change there. The spinning is directly related to the tangential acceleration or the linear acceleration of the falling mass. Now, if your attachment, if your rope was not all the way out to the outside, so let's do a side question. What if the rope was closer into the wheel? So what if the falling mass was over here? Okay. So is A directly related to alpha? Well, it's ralpha, right? If you put the mass closer in towards the axis of rotation, closer towards the axis of rotation, it's going to cause a smaller torque on the system. With less torque on the system, it's going to spin less. So it'll take more time to get down. Less acceleration. So if it's closer in, it's less acceleration. But in this system, all of the masses are the same distance away from the axis of rotation. Okay, so therefore the angular acceleration is directly related to the linear acceleration of the masses. So since C has the least inertia, it makes M fall the fastest, which means that C must also rotate the quickest. All right, here's question C. So this one will ask you, rank the three cases below based on which string has the greatest tension. Ooh, that's a great question. Go ahead and leave your answer in the comments below when I upload the YouTube video. Thanks for tuning in. I'll see you next time.